Welcome to Mathematics. Today we'll be solving the Pearson Edexcel IAL January 2023 paper of Physics Unit 2. In the first question, we are given this current against voltage potential difference graph for an electrical component, and we have to find which component this is. If I look in the features of this graph, we see that this is a constant gradient. The gradient over here is 1 by R. This is an IV graph, I against V. I know the equation V equals to IR. I have to move I to the left since this is compared to the y-axis and this is in the x-axis. So I'll put I on the left. If I make I the subject, I get V by R over here, or 1 by R times V. This can be compared to y equals to mx plus c. C over here is 0. So the gradient of this graph is 1 by R. If it has a constant gradient, the value of 1 by R is constant. If 1 by R is constant, R must be constant. Now we have to find for which component the resistance will be constant. For a diode, the resistance will change. For a filament lamp, the resistance will increase as we increase the voltage. This must be a resistor at a constant temperature. The resistance of thermistor decreases as we increase the temperature or voltage. If we increase the voltage, the temperature goes up and the resistance of the thermistor falls. The resistance of filament lamp increases. However, for a resistor at a constant temperature, the resistance is fixed. Now in question 2, we are given that a monochromatic light travels through air and enters a glass block. We have to find which of the following quantities do not change. We have to remember this fact: for any electromagnetic wave, its frequency is its identity. It does not change its frequency whatsoever. Its wavelength might change if it enters a different medium. Its amplitude might change. Its speed will change in a different medium, but its frequency will always be the same. Now on to question 3. We are given this glass air boundary where we have an angle of incidence I. Now we have the following statements about total internal reflection. We have to find which one would be correct. If we recall total internal reflection, it only happens when we move from a denser medium to a less dense medium. So the total internal reflection over here will only happen when the light is moving from a dense medium to a less dense medium. If we look at this case, the light is moving from air to glass. Air is less dense than glass. So in this case over here, total internal reflection will not be possible. If we look over here, A is the correct answer. The most common wrong answer might be this one over here. This is just the definition of total internal reflection. This is true. This is true indeed. But the problem is total internal reflection only happens when we move from a denser medium to a less dense medium. So if I was given a light ray like this, red one, then C would be the correct answer. However, we are moving from air to glass, so from a less dense medium to a denser medium. In this case, total internal reflection is not possible. Now in the next question, we have a question about diffraction grating. In this case, this is just a question about testing if we remember how the diffraction grating equation works. For the diffraction grating equation, n is the number of maximum it is. So we have our 0th maximum over here, or the central maximum. Then we have our first maximum where n is 1. Then the second maximum n is 2. Third maximum n is 3. So this is the value of n. D over here is the gap of the slit, or distance between the adjacent lines in a diffraction grating. So A is the answer. For the diffraction grating equation, the distance between the diffraction grating and the screen does not matter if we are finding the angle theta. So using the diffraction grating equation, we have no mention of the distance from the grating to the screen. D is not the number of lines per meter, it's 1 by that. So if the number of lines per meter was suppose x, D will be equal to 1 by x. And the final one, the order of maximum, this is the value of n, not D. Now for question 5, we have a pulse echo technique. We are given that a bat emits a pulse that travels to an object and it detects the reflected pulse 6.5 milliseconds later. We are also given the speed of sound. We have to find the distance. The distance will be half the distance covered by the light, or sorry, the sound. The bat is releasing a sound from here and the object is over here. For the sound to go and come back to the bat, it will first go to the object, so it will cover the distance d once, and then it will return to the bat, so it will cover the distance d twice. So the value of d will be half the displacement of the sound. Sorry, not the displacement, the distance traveled by the sound. The displacement would be 0. My bad. So the distance would be the distance covered by the sound, which is 640 into 6.0 into 10 to the power minus 3. We are converting milliseconds into seconds, and then we'll divide it by 2. So this is 340 multiplied by 0.0030. C is our answer. Now into question 6, we are given an LDR and we are told that the intensity of light incident on the light dependent resistor decreases. If the intensity of light decreases, the resistance of LDR increases. If the resistance increases, this is the LDR over here. Now if I see over here, the voltmeter is connected to the fixed resistor. So we have to use the potential divider circuit. The voltmeter reading V will be the resistance of fixed resistor divided by the resistance of fixed resistor plus the resistance of the LDR multiplied by the voltage of the cell or the EMF. Now in this case, R LDR, this value over here increases. If this increases, the denominator as a whole will increase. However, the numerator is fixed. So if the numerator increases and the denominator stays the same, the value V will decrease. So the voltmeter reading should decrease over here. Option B and C are out of the question. We are left with option A and D. Now in this case, if I use the equation V equals to IR, now I'll make I the subject. We have the equation V equals to IR, I is equals to V divided by R. The total voltage of the circuit, this is not this V. This V over here and this V over here is different. This is the V cell value. The V cell value is still the same. However, the total resistance of the circuit, which is R, resistance of the fixed resistor plus resistance of the LDR, this is R, the total resistance of the circuit, this also increases. If this increases, the current will decrease since the denominator is increasing. So both the current and the voltage reading decreases, so A is our answer. Now we are given a question about spectra. We are given that electrons in this atom are excited to the energy level n equals to 3. So it's excited up over here. We have to find how many different frequencies of radiation can be emitted over here when it's returning. When it's returning, it can go directly over here. This is one of the possibilities. The next possibility would be going over here, and then from there we go over here. So we have a total of 1. This is one frequency that's possible. This is another energy level gap that's possible, and this is the third one that's possible. We don't have any other option, so 3 is our answer. Now in the next question, we are given a question about longitudinal waves which pass through a material, and compressions and rarefactions are formed. We have to find which of the following statement is correct. If I look at the first option, it says that compressions are where the displacement of a particle is maximum. This is wrong. If I compare two cases, so this was before the wave formed, and after the wave formed, this is the compression, this becomes the rarefaction. If I look over here in the compression, the displacement of the first point over here will be 0. So its displacement is 0. The displacement is 0 at compressions. It's not maximum. Now in the next case, in the next option, we are told that compressions are where pressure is a minimum. This is wrong. In compressions, a lot of particles come close together. They become compressed. If particles come close together, the pressure increases. The pressure will be a maximum at compressions. The opposite is written over here. This is wrong. In option C, we are given that rarefactions are point where the displacement of particles is a minimum. This is also wrong. For longitudinal waves, at compressions and rarefactions, C stands for compression, R stands for rarefactions, displacement is 0. The displacement is maximum at the midpoint between a compression and a rarefaction. Now in option D, we are told that rarefactions are point where the pressure is a minimum. This is correct. At rarefactions, the points are spread out. If the particles are spread out, the pressure decreases. So at rarefactions, the pressure is a minimum. This is correct. Now on to question 9. We are given a circuit with a lamp connected. We are told that the cell has negligible internal resistance. We are given the voltage or EMF of the cell. Then we are told in 30 seconds, the charge passing is 0.4 coulombs. We have to find the energy in joules. We have the voltage and the charge. We have to find the energy. We know that a voltage or potential difference or EMF is basically energy per unit charge. So voltage is energy divided by charge. I know the voltage and the charge. I have to make E the subject from here. The energy E will be V times Q. We can also write the energy down as work done or W. So the work done or the energy transferred will be 1.5 multiplied by 0.4. B is our answer. We are not requiring the time over here. It's just given over there to throw us off. Now for the last MCQ, we are given which of the following is not a correct statement about stationary waves. The first one is correct. All points between two adjacent nodes are in phase. So these are two nodes. Between this point, the waves move together. So they go up together, they come down together. This is correct. Antinodes are point of maximum amplitude. This is also correct. We have to remember this definition. Antinodes are where the amplitude is maximum. Nodes are where the amplitude is minimum. Now for option C, I can draw a stationary wave. This is a stationary wave. This is a representation of a stationary wave. This is a node. This is an antinode. I'll do the antinodes in a different color. In option C, we are told that the distance between adjacent nodes is equal to 1 wavelength. Over here, the distance between adjacent nodes will be this distance over here. If I look closely, this is half a wavelength, not a full wavelength. This whole length is 1 wavelength, and this blue one is half of that. So the distance between adjacent nodes is equal to half a wavelength. So this given option is wrong, so this is the answer. If I explore the last option, we are told that the net energy transfer along a stationary wave is 0. This is true. In stationary wave, energy is trapped between two nodes. So the energy is trapped over here along this length. It does not move to the left or right. Now moving on to section B. For question 11, we are given a particle traveling at a speed over here, which is given, and we are given its de Broglie wavelength. We have to find if this particle has a mass equal to the electron mass. So I have to find the mass of this. So I'll use the de Broglie equation, which is lambda equals to h divided by mv, or h divided by p. The wavelength over here is 7.37 into 10 to the power minus 10. Planck's constant, or h, is 6.63 into 10 to the power minus 34. We have to calculate the mass, and the velocity of the particle is 9.89 times 10 to the power 5. From here I can move m over here and move the 7.37 down there. I'll get 7.37 into 10 to the power minus 10 multiplied by 9.89 into 10 to the power 5 over here. If I calculate this, I'll get the mass. So the mass comes out to be 9.10 into 10 to the power minus 31 kg. Now to compare it, I'll have to go to the last page of our question paper where the mass of an electron is given. So if I go down there, over here the mass of an electron is 9.11 into 10 to the power minus 31. We got our answer to be 9.10 into 10 to the power minus 31 kg. These values are almost the same, so we can say that the statement over there is correct. This is 9.11 into 10 to the power minus 31 kgs. Therefore, this particle has a mass equal to the electron. Now moving on to the next question. Question 12 is about light waves. In the first question, we are given the angles over here, and we have to find the refractive index. Now we cannot directly put in sine 32. This is not the incidence angle. For the incidence angle, we need the angle with the normal. So we have to draw the normal at first. This is the normal over here. The angle of incidence is the angle between the normal and the light ray. So this is the angle of incidence I. Now the normal is always perpendicular to the surface. So this whole angle over here is 90. So we can find the angle I from here. I plus 32 is equal to 90. I find the angle of incidence I from here, which is 90 minus 32, which would be 58 degree. The angle of refraction will be this angle over here. It's the angle between the refracted ray and the normal. This is angle R. This whole thing is 90 degree as well. So R plus 50 degree equal to 90 degree. R is 40 degree. Now I have the angle of incidence and angle of refraction. I can use that now to find the refractive index, which is sin I by sin R, which would be sin 58 degree divided by sin 40 degree. If I calculate this, I get a value of 1.32. This is the refractive index of the glass. Now on the diagram, we have to draw the ray of light as it emerges from the prism at A. Before I draw that, I'll draw the normal to it, so it gets easier for me to see what happens. This is the normal, which should be perpendicular to the surface. Over here we are moving from a dense medium to a less dense medium. In that case, it will refract away from the normal, so it will move like this. This will be less pronounced, so somewhat like this. We have to ensure that this angle over here is larger than this angle. This is a must. Now in the next question, we are given that a different prism is made of glass with a refractive index of 1.63. We have to calculate the speed of light in the glass. The refractive index is also equal to V1 by V2. In this case, which would be the velocity of light in air divided by the velocity of light in glass. So 1.63 will be equal to the velocity of light in air, which is c, or 3 into 10 to the power 8, divided by the velocity in glass. From here I can find the velocity of light in glass. This will be 3 into 10 to the power 8 divided by 1.63, which would be 1.84 into 10 to the power 8 meter per second. Now moving on to question 13, we are given two equal lengths of two copper wires W and Z, which are connected in parallel, and we are given that wire Z has twice the diameter of wire W. We have to explain why the drift velocity of the charge carriers is the same in both the wires. In this case, we need the help of two equations. One is I equals to NA VQ. The other one is that the resistance is rho L by A. The change over here is in the area. If the diameter is doubled, the area will be quadrupled, because area over here, or cross-sectional area of the wire, is equal to pi times d by 2 square. So the cross-sectional area A is pi d square by 4. Pi by 4 is a constant, so area is proportional to d square. Here the diameter of Z is doubled, so the area of Z is 4 times the area of W. So area of Z is 4 times area of W. Now if the area becomes 4 times bigger, the resistance becomes 4 times, or 1/4. So for Z, the resistance is 1/4 of W. And we'll write down the reason as well. This is because it has 4 times the cross-sectional area. We also know that V equals to IR, or I equals to V by R. The voltage over here is constant, since this is a cell and we don't have to divide the voltage over here. The voltage is the same. However, for Z, the resistance is 1/4, so the current will be 4 times bigger in Z. So if I look over here, the current for Z is 4 times the current of W. The area in Z is 4 times that. So this both cancels out. If I look closely, if I consider IZ to be 4 IW and AZ to be 4 AW, we have IW equals to NAW VQ. The charge and the number of charge carriers are also the same, since they are the same material. The resistivity is also the same, since it's the same material. Now for Z, this will be IZ equals to NAZ VQ, which is 4IZ equals to 4AZ VQ. We have 4IZ equals to 4 times NAZ VQ. We can cancel the 4 out. If I do that, I get IZ equals to NAZ. Sorry, my bad. If I write 4 down, this will be W. This is 4IW equals to N times 4AW times VQ. I can cancel the 4's out. I'll get IW equals to NAW VQ. This is the same equation, so the value of N, V and Q are still the same. or since I know that N and Q are the same, V must be the same. Now for part B, the wires are connected in series now. I have to complete the table by placing a cross in the correct box for each quantity. Since they are in series, the current across the wires will be the same. So this. Now they are in series. The resistance will matter on rho L by A. They are the same length, they have the same material, so rho L is a constant. So their resistance is inversely proportional to their area. So the greater the area, larger the value of resistance. Over here, my bad, the greater the area, the smaller the value of resistance. For Z, the area is larger, so the resistance is smaller. So the larger value will be for W. For W, the area is smaller, so the resistance is larger. So resistance is larger in W. The potential difference will also be dependent on the resistance, since this will act like a potential divider. So VW will be RW divided by RZ plus RW plus the resistance of fixed resistor as well, times the voltage of the cell, and the voltage across Z will be RZ divided by RZ plus RW plus RF times V cell. Both of the expression only have one difference, it's in the numerator. Everything else is the same. From beforehand we know that the resistance in where W was bigger, so the voltage across where W must be greater as well. So potential difference across W is larger. Now there will be a difference in the drift velocity since they are in series now. We know that I equals to NAVQ. The current across both of them are same. N is the same as well. N is same. V is what we are finding stuff about, and Q is the same. N is same, Q is same, I is same for both of them. For the only difference is due to A. If I make V the subject over here, I'll get I divided by NAQ. Only A is the variable over here, so I can separate that. So I equals to NQ multiplied by 1 by A. Or we can write down that V is proportional to 1 by A. For W, the area is smaller, so the drift velocity is bigger. So the drift velocity will be bigger in W. Now moving on to the next question. We are given a circuit shown to investigate the properties of a negative coefficient thermistor. All thermistor we learn in this syllabus is our negative temperature coefficient. The negative temperature coefficient basically means that as temperature increases, the resistance decreases. So there's an inverse relationship between the temperature and the resistance. There are also positive temperature coefficient thermistors, but we do not learn of them. They are the opposite. If we increase the temperature, their resistance increases. So basically things like filament bulb. Now we are given this circuit. The cell voltage is 12 volt. We are given two resistors in parallel over here, and then a thermistor in series with them. We have to find the voltage across this parallel combination. In this question, we are also given the ammeter reading, which is 23 milliamperes. So 23 into 10 to the power minus 3 amperes. The resistance of the parallel combination will be 1 divided by, so basically the reciprocal of the sum of reciprocals, or 1 divided by 1 by 500 plus 1 by 600. This will come out to be 273 ohms. We always add the resistance of parallel like this. So 1 divided by the sum of every resistance reciprocal, or 1 by the resistance. So R parallel for n things in parallel is 1 by R1 plus 1 divided by 1 by R1 plus 1 by R2 plus 1 by R3 and so on until the last resistor. So we know the resistance of this parallel combination. Using that and the voltage and current, I can find the resistance of the thermistor. We don't need that yet. For now, I have to find the voltmeter reading. The voltmeter reading is across this parallel combination. I know the resistance of this parallel combination and I know the ammeter reading. So V will be I multiplied by R. So 23 into 10 to the power minus 3 times 273. The voltmeter reading V will be 6.28 volts. Now in the next question we have to find the power dissipated. Now we need the potential difference across the thermistor. This will be the total resistance, total voltage, which is 12 volt, minus the voltage across this parallel combination, or 6.28 volts. This is the potential difference across the thermistor. This is 5.72 volts. We know the current as well. The power will be V multiplied by I. So power dissipated is 5.72 multiplied by the current, which is 23 into 10 to the power minus 3. The power will be 0.131 watts. Now for part B, we are told that the student decreases the temperature of the thermistor. We have to explain its effect on the ammeter and voltmeter readings. This is a negative temperature coefficient resistor, so we are reducing the temperature over here. If I reduce the temperature, the resistance will increase. So resistance of thermistor increases. Resistance of this parallel combination is still the same. So for the potential divider circuit, or the V value, this is the value of V is Rp, which is the resistance of the parallel combination, divided by Rp plus Rt, times the voltage of the cell or EMF of the cell, which is 12. In this case, everything else remains unchanged except the thermistor's resistance. This is increasing. If this increases, the whole denominator will increase. Everything else is constant, so the voltage must decrease, or the voltage reading over here will decrease, and this is due to the resistance of the thermistor increasing. So we start with what happens at first if we decrease the temperature, which is the resistance of the thermistor increasing. We can also look at this question in a different manner. That manner is that since the resistance of thermistor is increasing, the circuit resistance R is increasing as well. The voltage or EMF is still constant. So V equals to IR. I make I the subject. This will be V by R. The total voltage or EMF is unchanged. This is a constant, and the circuit resistance is increasing. So the value of I must decrease. Now the resistance across this parallel combination will still be the same even when the thermistor resistance is increasing. So Rp is constant, and we know that V is equal to I multiplied by R. The reading of V over here, the voltmeter reading, will be I multiplied by Rp. Rp is a constant, that's not changing. However, I is decreasing. If I decreases, the voltmeter reading will also decrease. So we state that the parallel resistor combinations resistance is still the same, it's not changing. However, the current is changing, and V equals to IR. So we know that V higher and the current decreases. Since this happened, the voltmeter reading V must decrease. So hence voltmeter reading will decrease. Or it decreases. And that's it for this question. Moving on to question 15. This is our 6 marker over here. Now we're told a story that a student connected a signal generator to a loudspeaker and arranged metal plates in front of the loudspeaker. This is a double slit experiment over here. We're told that the student left gaps between the metal plates. So these gaps, and the sound waves from the loudspeaker passed through the gaps, which were approximately the same size as the wavelength, so diffraction will be maximum. We know that from this part. Now we are told plan view over here. In this question it's not confusing, but there are some questions where we might be confused by this word. The word plan just means top, so this is the top view of the experiment. Now we told that the students stood at point X and heard a loud sound. X is the midpoint over here. So we have two diffracting waves coming from both of these points. Since X is at the center of them, constructive interference occurs there since path difference is 0. We'll talk about this in depth soon. Now we are told that the student walked in a straight line in the direction of the arrow, so upward. And as her position changed, the sound became quieter until she heard no sound. So she's going to the first minimum over here. We have to explain this with reference to interference. Now, since the wavelength of the sound waves and the gap size are almost equal, there will be diffraction. These waves will diffract according to Heinz principle and interfere with each other when they meet. So we start with diffraction. The waves diffract as they pass through the gaps. Now if I look at the path difference, the path difference is the difference in distance from these 2 points at a certain point. If I consider X for example, the path difference is the difference between the lengths of these two black lines. At this point, the difference between the lengths is 0. This line and this line are of the same length. So at X, path difference is 0. So constructive interference takes place. And when constructive interference takes place, the amplitude is maximum. Now as we move away from point X, so we go somewhere over here. Now if I draw the lines, this black line over here is smaller than this red line. The difference between them is the path difference. So if I draw a line that's 90 degree, this length over here is the path difference. We don't have to know the construction or what the path difference will be equal to. We just have to know that if it's not at the center, there will be a path difference. If path difference is a multiple of the wavelength, constructive superposition or constructive interference occurs. And if it's half more than a multiple of lambda or half lambda more than a multiple of lambda, at these places destructive interference occurs. So as we move away from X, the path difference increases from 0, and as we go on, there is a point where there was no sound. When there's no sound, it's when the path difference is n plus half lambda, so destructive interference occurs and the amplitude of sound is minimum or almost zero. So when the student moves away from x, his phase difference increases, and this keeps on increasing until there is a no sound when path difference is half lambda. Since this is the central maximum and this is the first minimum, at the first minimum n is 0, or n is 0, n plus half lambda is half lambda basically. So it increases until no sound is heard, and at the point where no sound is heard, the path difference is lambda by 2 and destructive interference occurs there. And this is how we answer it. So we'll go over our answer once again. We begin by saying that the waves diffract as they move through the gaps over here, this and this. Then we talk about how at x the path difference is 0 and hence constructive interference takes place. And when that happens, amplitude of sound is maximum. And then the student moves away from x and the path difference keeps increasing until no sound is heard. At the point that no sound is heard, or at this point, the path difference will be half lambda and destructive interference will take place here. We can also write down a final line that the amplitude of sound is minimum over here. Now moving on to the next question, part B of the same question. We are given that interference can be demonstrated by using visible light as well. We are given two filament bulbs which are connected to the same power supply. So they are in phase, or the light they emit will be coherent. And we have a screen placed at a distance. We have to explain why it is not possible to create a consistent interference pattern on the screen in this arrangement. Oh, my bad, I stated something wrong just a moment ago. They do not have to be coherent just because they are connected to the same power supply. There might be a delay for the light to go to filament lamp 1, or the filament lamp might take a longer time to heat up due to that current depending on its filament over here. So even the slightest change in the filament will cause it to not be in phase. So the sources are not coherent over here. It's not coming from the same place. And another issue is that for filament lamp, we don't have a monochromatic light source. We have several different colors over here. It is a mixture of several different frequencies of light. It's not a pure source of light with only light of one frequency. So that's another problem. This is how we structure our answer. We begin by saying that the lights are not coherent as they do not have a constant phase difference. Just defining what coherent is. And then we talk about how the light from the lamps are not monochromatic. And that's it for question 15. Moving on to question 16. We are given this question where a solar panel's dimensions are given. So it's 1.2 meters long and 0.8 meter wide. From here I can find the area. We are given the minimum power of 140 watts. We have to find the minimum efficiency of the panel that will operate the pump, given that the intensity of light on it is 1040 watt per meter square. The area of the solar panel is 1.20 multiplied by 0.80. This is a rectangle. Its area will be 0.96 meters square. The input power, total input power, will be the area multiplied by the intensity. The intensity of light is 1040 watt per meter square. We can work with this. We can work this out by simply looking at our units. We have meter square over here and watt per meter square over here. I want to find the power which is in watt, so I have to cancel the meters over here. I can do that by simply multiplying the area over here. So this meter square and this meter to the power minus 2 cancel out. We get an input power of 998.4 watts. Now we have the efficiency. We have to find that. Efficiency is denoted by eta. The efficiency is the output power by the input power. The output power that we need, the minimum output power, is 140, and the total input power over here is 998.4. So this will be the minimum efficiency that's required. The value would be 0.140. This is the minimum efficiency. We have to suggest two reasons why the value calculated in 1 is the minimum efficiency that will operate the pump. So this is the minimum efficiency that will operate the pump. We might need a greater efficiency as well. This is because at times the sunlight will not be perpendicular to the solar panel. It might be at an angle something like this, and if it's at an angle, the input power will decrease. It doesn't even have to be for that reason. Some of the light might be reflected off the surface of the solar panel, so we cannot observe all of the light, or we might be having clouds or rain or fog which will decrease the intensity of sunlight falling on the solar panel. So for that reason the input power will decrease, and if that decreases, the output power will also decrease. We cannot have an output power of less than 140 watt to operate the pump. So we'll write down any 2 points from there. The most obvious points are the fact that we might have a cloudy day. This is the most obvious point. The second most obvious point would be that light is reflected off the solar panel. You can write down any points as you want, since this is a suggest question. You can get creative with this. So the intensity might be lower due to clouds, rain, fog, any condition, and the light may be reflected by the solar panel. So not all of the intensity of the light is absorbed, some of it is reflected away. These are the 2 points, that this is the minimum efficiency, and it might actually be higher than that. We might need a higher efficiency for operating the pump. Now for part B1, we are given the difference between unpolarized light and plane polarized light. You need to remember these definitions. Unpolarized light is where vibrations are in all directions or all planes. And for plane polarized light, the vibration are all in one plane, and that plane includes the direction of motion. A plane is basically any 2D surface. This can be a paper. If you want to draw an unpolarized light, you cannot draw it on a paper accurately. You would have to use 3D representation. So if you wanted to draw it accurately, you need to poke a hole into your page and insert another page through it to actually represent what happens in unpolarized light. But for polarized light, I can just draw it on this 2D surface. So this screen is also a 2D surface, and this is a polarized wave. The waves are all in one plane. We do not have to have a 3D space to imagine this accurately. For example, I can draw a square pretty easily over here. I can draw a rectangle easily, but if I have a cube, this gets tougher. We can draw something like this, but this still isn't an accurate representation. This is just an drawing that will help us imagine what it could be in 3D space, but it's not accurately what happens. We'd need to think in a 3D space for that. Or we can talk about directions. So an unpolarized light has vibration in many different directions. These are the directions of the waves, and the wave is traveling from inside your screen to outside towards you. This is a 3D representation of a polarized, unpolarized light. For polarized, the direction of the wave or the direction of the vibration is only one. So there is vibration in one direction. In this case as well, the wave is coming from behind your screen towards you. In this case as well, it's perpendicular to the direction of wave vibration. So the direction of energy transfer or wave travel is perpendicular to the vibration. We can use either of the definitions. One is about the direction, one is about the plane. So this is one way we can write down our answer. We talk about how unpolarized light has vibrations in all plane. Plane polarized light has vibration in one plane. And the plane includes the direction of wave travel, or we can write it in terms of direction. This is the other way we can answer it, using the vibrations directions, not the plane. You'll have to remember either one of this, as this is a very common question in your A levels. Now we have a question where a student can demonstrate that the light from the sun is unpolarized. We have to devise an experiment which can show that. If the light was polarized, it only has vibrations in one plane. So if I have a polarizing filter over here, so polarizing filter like this, if I rotate the polarizing filter, at one point there will be no light that's passing through our filter, at other points there will be light passing through our filter with a greater intensity. So I'll keep rotating this. At some points it will have 100% intensity. It will be as clear or as bright without the filter as it is with the filter, and at other points it will be completely dark. This is if it is polarized. However, if the light is unpolarized, even if I rotate the filter, the intensity of light will not change, since there will always be light which is perpendicular to the filter's direction. Over here, if the filter is vertical, the light will pass through it if it's vertically polarized. However, if the polarizing filter is put horizontally, the light that's vertical will not go through it, and we'll see nothing over here. We'll see a black screen or a black color on the polarizing filter. We'll not see the light. However, if it's unpolarized, if I have it vertically, the vertical component will go through and the horizontal will not. And if it's kept horizontally, the horizontal component will go through, the vertical will be stopped. So all I have to show is that if I rotate a polarizing filter, the intensity is unchanged. That will show that the light from sun is unpolarized. So we write this answer down. At first we said that at first we speak about how we will view the light of the sun through a polarizing filter, and that if it's unpolarized, we'll give the observation. Since we already are given the fact that sun's light is unpolarized, all we have to do is demonstrate that. So we can say that there will be no change in the intensity of light as the filter is rotated. And now we have to give the point of what it would be if it was polarized. So if sunlight was polarized, what would actually happen? The intensity would change as the filter is rotated. So this case over here would happen if the sunlight was polarized. Now moving on to question 17. We have to show that for this circuit, the resistance is this expression over here, the EMF divided by I minus the internal resistance. We can use Kirchhoff's second law over here, that in a closed loop, the sum of EMF is equal to the sum of potential differences. Over here, EMF will be IR, I times capital R plus I times small r. I can take I common over here, So EMF will be I multiplied by capital R plus small r. From here we can have EMF divided by I is equal to capital R minus small r, plus small r. And from here I can make capital R the subject. I'll get EMF divided by the current minus the internal resistance to be the resistance of the variable resistor. So we have shown that over here. Now we are given a graph of R against the reciprocal of current, or 1 by I, which is a straight line over here. We have to find the values of EMF and R from here. In this case, R is the subject, 1 by I, R against 1 by I graph. So if I change this over here, capital R is 1 by I, EMF multiplied by 1 by I minus small r. If I compare this to y equals to mx plus c, R is y. We see that over here R is in the y axis, 1 by I is in the x axis. 1 by I is x. EMF is the gradient and minus R is the y-axis intercept. So the EMF will be the gradient. For the gradient, I'll take 2 points over here. So one over here, this point is 8, 10. This point over here is 0, minus 2. This is x1, y1. I'll take this as x1, y1. I'll take this as x2, y2. It doesn't really matter which I take as 1 and which I take as 2. The gradient is y2 minus y1 divided by x2 minus x1. y2 is 10, y1 is minus 2. So we have 10 minus 2. x2 is 8, x1 is 0. So we have 8 minus 0 over here. We get 12 by 8. This is 1.5 volt. This is the EMF. Now minus R is the y-intercept. The y-intercept in this case is minus 2. So minus R is equal to minus 2. R will be 2 ohms. We have to state the units as well. Now for part C, we are told that the student suggested the power dissipated by the internal resistance decreases as the resistance over here increases. If capital R increases, we know that V is IR. For here, the equation is for the whole circuit. Now if the circuit's resistance or total resistance increases, its current must decrease, since we have to have the same value of V. So if R becomes double, or the total resistance, not this R only, this is R total. If this becomes double, the current in the circuit will become half. And we know that the power is I square R. This is the power dissipated by internal resistance. The value of I decreases while the value of R remains the same, so the power will also decrease. So if I write this down, so we start by talking about how the current in the circuit or I decreases as the resistance or R increases. And we know that the power dissipated by internal resistance is given by this formula, P equals to I squared times R small r. If you write down capital R over here, you lose marks. And we know that there is a decrease in I. If the value of I decreases, the power dissipated over here by internal resistance will also decrease. Hence, the student's suggestion is correct. Now, we are told that in part D, a student added a second identical cell in series with the first cell and repeated the experiment. If that happens, the EMF has now doubled. EMF will double. So the gradient must be doubled as well over here. So it will be twice as steep. And since an identical cell is attached, before this the value of R was 2 ohm. If we have two of the identical cells, we will have a value of R which is 4 ohm. So the y-intercept in this case will be -4. This will be our y-intercept, and the gradient will be twice of this. So we'll have a straight line through here that goes like this. This is the graph for part D. Now on to question 18, the last question of this paper. We are given a question about the photoelectric effect. We are given that photoelectrons are released with a maximum speed of 3.51 into 10 to the power 5 meter per second. We have to calculate the energy of these photoelectrons in electron volts. So firstly we can find the kinetic energy, which is half mv square. These are electrons over here, the mass of which are known. We are given the mass of electrons in the last page, which is 9.11 into 10 to the power -31 kg, and the velocity is 3.51 times 10 to the 5. This is squared. The kinetic energy comes out to be 5.60 into 10 to the power -20 joules. Now we have to convert this into electron volt. To convert this into electron volt, we have to divide by the charge of an electron, which is 1.6 into 10 to the power -19. We get the value in electron volt like this. This is 0.35 electron volts. Now in part 2, we are given the work function of some metals. We are given that the ultraviolet light used in this experiment had a wavelength of 310 nanometer. We have to find which of the metal was the most likely. From the wavelength we can find the energy of the photons. The energy would be hc by lambda. The main equation is h times frequency, Planck's constant times frequency, but we also know that the frequency is the speed of light divided by the wavelength for electromagnetic waves. So we have hc by lambda. So the energy of the photons would be 6.63 into 10 to the power -34 multiplied by 3 into 10 to the power 8 divided by 310 nanometers, so 10 to the power -9. So the energy of the photons are 6.41 or 6.42 into 10 to the power -19 joules. If I use one decimal more, we get 6.416 into 10 to the power -19. This is the energy of the photons. This will be equal to the work function plus the kinetic energy or maximum kinetic energy. We already have the maximum kinetic energy from part 1. This is 5.60. This is 5.61. If I take one more decimal place, this will be 5.61 into 10 to the power -20. From here I can find the work function. This is 6.416 into 10 to the power -19 minus 5.61 into 10 to the power -20. This is 5.86 into 10 to the power -19 joules. So the closest value to 5.86 is 5.89, which is for magnesium. So this metal plate was most likely made of magnesium. We write down our statement that the metal used is magnesium. Now for part B, we are given that we're told that photoelectrons are only emitted from a given metal surface if the frequency of the incident radiation is above a particular value. We have to explain why. In this case, we have to explain the particle nature of light over here. So we begin by talking about how each photon only interacts with one electron. Then we'll talk about the energy transfer. All of the energy of the photon is absorbed by the electron, and the minimum energy required is the work function. The electrons absorb the energy of the photons, and it requires a minimum energy to be emitted. We can also talk about how this is called the work function. Required to be emitted. After that, we'll talk about how E equals to hf. So the energy of the photon depends on the frequency. So E is equals to hf, hence the energy of the photon depends on its frequency. And then we finish it off by talking about how increasing the frequency is, or to increase the photon energy we need to increase the frequency. So just touching about how E is proportional to the frequency. So increasing E will require an increase in F. Now for the last question, we are given a statement made by a student. The student says that it does not matter what the value of the work function is for a particular metal. Photoelectrons can always be released if the intensity is high enough. We have to criticize this. If we read this, the student's statement talks about the wave nature of light. However, photoelectric effect displays the particle nature of light. If light behaved as a wave, this is true. This would be true if light behaved as a wave over here. However, it does not. It behaves as a particle in this scenario. The intensity is related to the number of photons, not the energy of the photons. However, to emit the photons, the energy needs to be more than the work function. So even if I shoot 1,000 low energy photon at a metal surface, photoelectric emission won't take place. However, if I send just one photon but it has sufficient energy, it will cause photoelectric effect. So the number of photons that's reaching the surface does not matter in this case. So we talk about how the intensity is related to the number of photons incident per second, and that it has no effect on the energy of an individual photon. And that's it for this paper.